Half the batch was hired by Air Force and half the batch was hired by DGCA. So complete 100% placement. And since then, we have had such a close relationship with Air Force and lately with DRDO. So I'm very, very happy that this relationship has lasted for 6 decades now, and it's only becoming stronger. Now, coming to UAV, I think UAV is certainly the technology of the future. In fact, I would say technology of the present. And the kind of uses that UAV has been put into, whether it is security of our borders, whether it is delivery of emergency goods, whether it is monitoring things in a crowd, whether it is there's just so many different uses people are doing. Not to forget taking photographs in a marriage. That I think this is really going to make or break our defenses particularly. It is not possible to monitor, let's say, our borders, with humans posted all over the place. Something that can be very easily done with UAVs. So I'm so happy that the department, with the help of Aeronautical Society of India and DRDO, is organizing this. It is sad that people cannot come to campus right now, and we cannot see all these designs in person and see them flying as Air Commodore Ghuratia talked about. But I'm sure next year we would be able to do in person, on campus contest on this. I really look forward to seeing some of these entries, see the presentation. And thanks for all the judges from IITs and DRDO and other places who are going to evaluate this. Once again, congratulations to all, and thank you very much.
Thank you, sir, for enlightening us with your presence. Next, I would like to welcome our guest of honor for today's event, Air Marshal Retired R.K.S. Khera, sir. As Director Sir mentioned, Sir did his graduation in electrical engineering from IIT Kanpur, and during his career of 38 years in Air Force, Sir was awarded with Vishisht Seva Medal and Ati Vishisht Seva Medal by the President of India. Sir, I would request you to please share your insights with us.
Directors, Punjab Engineering College, Dr. Dheeraj Sanghi, the Head of Department Aerospace, distinguished guests today, especially Marshal Sushant Singh, AOC 3BRD, all the faculty members who are participating, all the students, and the well, it's a matter of indeed a great pleasure for me to be sitting here today online and saying few words on this particular event of UAV design competition, which has been so successfully conducted in spite of the ongoing pandemic. In fact, I recall last year on 6th December, when we had a 3BRD NTC National Symposium, that when I was delivering my talk, I had talked about the UAV engineering in particular and the opportunities which we have in this particular field of aviation. I'm really glad that in spite of all these issues of COVID, the college has been pursuing it. And I was in touch with the HOD, and Dr. Jindal had been talking about it quite a bit. Though, of course, we could not have the physical contest, but in spite of that, it is heartening to see that a huge number of participants, enrolled 30 of them, out of which 15 were shortlisted and finally 5 are the finalists. Well, it's indeed also a great pleasure for me to conveying my best wishes to the college, which is completing its 99 years, already completed on 9th of November. And this is the centenary year for our great college, college. As the director talked about the historical linkages, yes, we have huge link with the Engineering College, in particular Department of Aerospace. In fact, our first batch aerospace engineers, the 3 of them who joined the Indian Air Force, and not getting our mentors, our first AOC in C, AVM Harjinder Singh, who was a graduate of the then Maclean Engineering College when it was at Lahore. So in his 20s, he joined the college, and thereafter he was one of the main engineer, the aviation engineer, aviator, himself a flyer, who contributed a lot, not only in the Indian Air Force defense sector, even in the civil as well. He's the one we are proud of who designed and flew the machine. In fact, one of the aircraft which is lying in Punjab Engineering College Department of Aerospace is the first aircraft, Kanpur 1, which he himself designed, manufactured, and he flew. And if I say that, he flew, in fact, from Kanpur in the same aircraft and brought it to Chandigarh and gave it to his alma mater, gave it to Punjab Engineering College. And we, in fact, in the Indian Air Force, we feel very proud that we have a long association with the Punjab Engineering College. Well, as far as the UAVs are concerned, I'm not going to talk much on this. It is one area where a lot can be done because its utilization is not only in the defense sector, but all over. In fact, I talk about the search and rescue, the agriculture areas, the jungle maintenance, the wildlife preservations. You name it, I think it is being used. Artificial intelligence in this, the navigation these days, the UAVs are navigating without the GPS. You know, you just put the imagery and you're able to move around in the thick jungles and do various jobs there. The facial recognition, the security cameras installed can look into a particular person, and thereafter, in any thing, it can monitor, it can see if anything untoward is happening. Another area which is very interesting is the biomimicry. Biomimicry is where the robotic birds are being made as a prey birds, and we use them in aviation in the airports to scare the birds. And, this is another very important thing for the agriculture sector, where this can be used if it's low cost. The robotic bird, it can be used to save your agricultural produce as well. As far as the platforms are concerned, today you name a thing, it's happening in the UAVs. And beautiful things are happening now is a lot of adaptive manufacturing is going on in the UAV sector. Another area where our academia as well as R&D can look into it. As I keep talking about our Air Force Nodal Technology Centers, which we have created, which is nothing but a triangle of academia, R&D, industry, and Indian Air Force. This is where I urge my Air Force partners to look into more seriously into it. Chandigarh is very lucky. We've got everything here. We've got CSIO, the best of the R&Ds as possible there. We've got Bell next door. We have the academia, the engineering college. So this is one of the best places where a lot of things can happen in the area. And I wish and I hope things do take a shape. The government of India has a number of initiatives under Atmanirbhar India, the slogan of the Prime Minister. A lot can be done in that. A number of policies are being changed, including FDIs. So if we sit together, if somebody becomes the integrator, like I said, 9 BRD or 3 BRD, if they take the integration part of it, and we take academia along with us, the R&D along with us, lot can be, including the printing itself. So I first of all compliment the college for conducting such a wonderful competition, and I hope and I wish we don't only talk, we also deliver something in a reasonable time frame, and that would be a great thing for Chandigarh as well. So my best wishes to all the organizers, all the students, all the alumni available today on this, and the faculty members. Thank you very much. God bless. Thank you.
Thank you, sir, for such encouraging words. Next, I would like to introduce our second guest of honor, Air Marshal retired Sukhchand Singh, sir. Sir has done his post graduation in integrated electronics from IIT Delhi. During his career of 36 years in the Indian Air Force, he was awarded with Vishisht Seva Medal and Ati Vishisht Seva Medal by the President of India. Sir, I would like to request you to encourage us and the participants with your kind words.
Uh, Thank you. I I have a little problem with the internet because I think the electricity is going and coming. So without any so-called online UPS, maybe I'll get disconnected in between. Can everybody see me and hear me?
Yes, sir.
Yes, sir.
Thank you.
Yes, sir.
First and foremost, thank you very much for this invite. And it's a great thing to know that Chandigarh is becoming part of the national airfaring endeavors of the country. So today, when I see Aeronautical Society along with DRDO pushing in for such competitions, it's a matter of great joy. UAVs particularly are going to be the call of the day. The time between concept to the final productionization of that concept has reduced tremendously. In fact, a few days back, I was talking about tiny ML, that is tiny machine language, which can be now put into small chips and they can go as close to the sensor. With that, the UAVs now become a great potential in which they can be more autonomous. So today, when we talk about UAVs, the competitions will not only be related to the vehicles per se, which in any case is always a challenge. And all the aeronautical engineers will always strive to get some exotic and novel aeronautical structures which can meet the mission requirements. The first thing which comes to the mind is morphing of wings. With technology now available, morphing of wings will be a great challenge. And depending upon the mission, one can actually look toward these things. UAVs are very diverse. So when we have competitions, the mission of the UAV plays a very important role. This mission will be very important to ensure that the final outcome of the UAV design is achieved in the shortest possible time and with most optimum resources. UAVs today are going to become a UAV for service. That is, it will become a service like cloud and other softwares. Like everybody was talking about leasing. You will have a huge amount of opportunities for leasing such UAVs to the armed forces, paramilitary forces, medical and health organizations in the country. It's very heartening to note that we have moved away from just flying of UAV competitions to designing and concept of UAVs, which, like everybody else has been talking about, once the COVID-19 actually is behind us, productionization and meeting in person to see that those concepts of UAVs to achieve the so-called mission will be a treat to watch. I wish those 15 participants who have been able to make it to this concept round all the very best. And I urge Punjab Engineering College, along with the Aeronautical Society of India and DRDO, to make new ventures into the UAV designs. And one day, who knows, the design which actually surfaces out from Chandigarh would be an international Atmanirbhar design. Thank you. With that, I wish everybody all the very best. Thank you very much.
Thank you, sir, for such insightful discussion. Now, I would like to request Mr. M.S. Rajeshwaran, sir, coordinator for today's event, to say a few words.
Very good morning to everyone. Uh, Honorable Chief Guest Air Commodore Sanjeev Guratia, respected Guest of Honor, retired Air Marshal R.K. Shera, PVSM, AVSM, VSM, and Guest of Honor, retired Air Marshal Sukhchain Singh, AVSM, VSM, respected Director Sir Professor Dheeraj Sanghi, dear colleagues, students, and my dear all the participants, it is my privilege to be the one who is making the closing remarks and the vote of thanks in this extraordinary event. It is extraordinary in the manner that we have gathered and in the manner that we are conducting this competition. On behalf of the coordinating team, our department, and PEC as a whole, I would like to thank our Honorable Chief Guest, the Chairman AESI of Chandigarh chapter, for your generous support and encouragement to conduct this competition, sir. Thanks also for enlightening us with the possible technological schemes available for the young innovators in PEC and in India as a whole. This event would have not been possible without your generous support, sir. Thank you. In the same beat, I would like to extend my sincere thanks to our guest of honors for your kindness and continuous support to our department. We are so fortunate to have you all, sir. I sincerely thank our director, Professor Dheeraj Sanghi, for his motivation and providing us the confidence in online realm. And I would like to extend my thanks to our judges for your continuous effort and support for making this event possible. Most importantly, my hearty thanks to all the students, participants, the coordinating student members for making this event successful. So I wish you all the very success and an eventful day. Jai Hind.
Thank you, sir. Energetic words can unfold hidden power of mind. On this note, we would like to proceed with the presentation round. I'd
Manani,
request, yes, sir.
hello. Can we rise
Sir?
for the national anthem, please?
Yes, please.
Yes, sir.
Anybody to start with? You can start.
Shall we play?
Yeah.
भाग्य Thank you. So once again, thank you very much all. Over to you, sir, Pansar, for the evaluation round.
All right. A very good morning to all the members present and the participants. So before we start today's session, I would first like to give a brief overview about the scheme that we are going to follow and the rules and regulations regarding the presentation. So as you have already heard from our chief guest, there were 30 entries in this competition, which were shortlisted to 15 by a scrutiny of the reports. And then based on a further deeper scrutiny, out of these 15 reports, 5 teams have been shortlisted today to make the final presentation, of which 3 teams are going to be declared as the prize winners. Now, since the judges have already gone through in detail all the reports of the participants, therefore, we have allotted a time slot of 5 minutes only for each team to highlight their design. So they have been told that they will be given 5 minutes to present their idea. They should focus more on the innovation aspect of their design, on the feasibility of their design, and also bring out the special features of their design to address the problem statement that was presented in the competition. So my request is, please leave out all the details regarding the analysis that you have done, or the calculations, or the sizing procedure and the numbers. Those are not really very important. We are interested more in understanding your logic and your thought procedure behind coming up with the design. So that's why we are going to give you 5 minutes and 5 minutes only. And any team that exceeds 5 minutes is going to be severely penalized, because this has been made very aptly clear. In fact, 4 out of 5 teams have also modified their presentations based on my feedback, that in 5 minutes you cannot present 30, 25, 30, 22 slides. So many of them have. One team has said that they will still manage with 22 slides in 5 minutes, which is okay. We are okay with that. So remember that. Now, I would like Mr. Lekhi to show his video, and also Mr. Saurabh Bagare from Singapore. You can unmute your viewer, Saurabh, if you are there. So yeah, that's welcome,
Hello.
Saurabh. Welcome, Saurabh.
Am I audible? Am I audible?
Absolutely
Yeah.
audible, loud and clear. Great. So 3 of us are going to be judging the entries, and in the end, we are going to compile our scores and come up with the list of the winners. I have already received the presentation of all the teams. So I will allow you to share the screen, but in case you face any problem, which happens very commonly, then I am going to show the PPT from my laptop, and then I'm going to ask you to talk about it. Okay. We are going to go in a random order. I also want to introduce our timekeeper, Mr. Nomanuddin. Nomanuddin, if you are there, can you please?
Yes, sir, I'm there.
Yeah, very good. So Nomanuddin is going to keep time, and he's going to give a warning sound at the end of 4 minutes, so that you have 1 minute available to wind up your presentation. Okay. So with that, I think we should quickly start with our session. And to begin with, I'd like to, just a minute, I'd like to invite Team Technique, that is led by Joshit, to start their presentation. So the moment they start, you can share your screen. I'm allowing you to share your screen. Yeah, you can share your screen. So Team Joshit, that's very good. The moment you start speaking, Nomanuddin is going to start the timer, and then at 4 minutes, you'll get a warning. And at 5 minutes, we are going to ask you to stop your presentation. Okay. So if you are ready, Team Technique.
Hello.
Are you ready?
Hello, sir. Can you hear me?
Yes. Are you ready to present?
Yes, we are ready to present, sir. Can you see the screen that we are sharing right now?
Make it full screen. Your screen is visible, but not full screen. Yes.
Thank you, sir. Is it now full screen visible?
Yes, now it is visible. The moment you start speaking, Nomanuddin, you can start the timer.
Okay, sir.
All right. So we'll begin?
Yes, please start.
All right. Good morning, everyone, and all the dignitaries. First of all, we would like to thank you for giving us this opportunity. The figure that you see here is what we are trying to present is a very novel tilt wing and tilt rotor design and we are going to speak about what's so novel about it. But first of all, we'd like to give you a visualization. What's a vertical takeoff and landing? So the need for vertical takeoff and landing came from the fact that fixed wing has a very little agility but high endurance. However, uh, rotor wings such as helicopter or quadrotors have more agility but a little bit less endurance. So how about we mix and match? So that was the idea. But the main concern for a VTOL is this phase, the transition mode. How do you move from a vertical takeoff and to cruise condition and vice versa? Also, there are aerodynamics challenges. For example, endurance, but there are slip strings from the rotors. Also, rotors have a lot of efficiency loss. So how do we cope with this trade-off? First of all, to address this issue and to make the agility and the issue of endurance, we came up with this design of having simultaneous tilt rotor and tilt wing. By keeping manufacturing and the what do I say, the number of component to be reduced, we designed this mechanism that could simultaneously control the wings, as well as if you see the top view of the mechanism, there will be servo that will control the tilt rotor. In the video, we saw an independent control of both tilt wing and tilt rotor. The video is, of course, the prototype that we have tested in wind tunnel. The final next stage beta phase model is what you see in this green and black colored configuration. Of course, this gives us an agility of 4 configuration: cruise, tilt wing, tilt rotor, as well as tilt wing and tilt rotor simultaneous control. We also have designed a drop mechanism which has a variable door dock that can take out different kind of payload. So it's a user customizable payload with a variable drop mechanism. It means that this drop can change its rail, and there will be door that can open up at different kind of width of the payload. Our unique selling point is that we provide a very modular wing and tilt structure. The modularity lies in the fact that these wings and this tilt can be taken out like a plug and play device. That's what we have kept in mind while designing. This is highly endurance and highly agility because, for example, in tilt rotor, in only quadcopter, the agility is defined by changing the direction, changing the RPM of the motors. And for wing is having the flaps. However, here we can just directly change the angle of attack of both the rotor or the wing to change the direction. So that's quite agile. For example, something similar to that of a hummingbird. We have a long range, and our payload capacity can vary from 600 to 1 kg at a cruise speed of 500 to 5 meters per second to 10 meters per second. We have kept all this design by keeping minimum in mind. So this is the minimum, bare minimum we provide at 60% throttle. So if we increase the throttle or the speed of the cruise, we can increase more of the payload capacity. We did several testing of the motor and the propeller combination and came up with this fact that after doing a wind tunnel, we get 60 to 70% more payload carrying capacity compared to having the same tilt rotor without wing. The choice of wing was also very interesting. We kept coefficient of moment very less in mind. So, and also a trade-off between the lift to drag ratio. So that's the kind
4
of,
minutes are over, 1 minute is remaining.
thank you so much. That's the kind of design that we were aiming for. In future, we want to build the controller because the controller here we think is going to be really important. However, not just the controller, we have planned another thing. On the fuselage, we'll have a sliding mode payload. So instead of keeping a fixed battery position and ESC's positions, we'll have a mount that will slide according to the change in the center of gravity. So that will give us a very one directional controllability. If we can have that, then the entire controllability of the the aircraft based on sudden gust of wind can also be neutralized. Thank you for listening to us, everyone. Here is our contact information for our future references. If you have doubts, please.
Thanks a lot for your presentation, and thank you so much for maintaining the time limit. It's a very good start.
Thank you, sir.
I would like to invite Shri Deepak Lekhi if he wants to start with any questioning, and then we'll move to Saurabh Bagare. Deepak ji, would you like to ask any questions to Team Techunique? You are on mute, sir. You have to unmute yourself.
Sorry, sir.
Huh.
Sir, my first clarification is the range of payload they are trying to get us.
Deepak, sir, I cannot hear your voice clearly. Can you please speak
What is
again?
the range of payload you are planning to do? The range.
I'm sorry,
So,
sir.
so how much is the payload?
Okay, the payload is around 600 to 1 kg we can take.
Look, when you do design, and if you say that the payload is 600 to 1 kg, immediately it raises a question on
Yes.
your calculation and your feasibility, because 600 to 1 kg is a very large range for a person to say about the payload. If you had said 600 to 650 kg, 650 grams, I would have understood. Okay. Anyway,
All right.
so Deepak ji, his answer is that it can carry a payload of 600 grams to 1 kilogram.
And what is your all-of weight of this UAV?
Deepak, sir, I cannot hear.
What is the all-of weight of your UAV?
Yeah, the all-of weight of the UAV will be around will be around, if I consider with payload, 2 kg, but only the UAV will be around 1 to 1.5 kg.
So, okay, so that means around 50% of the weight you can cut it to payload. If it takes max for both.
Yeah, so his question is that with 50, you are having a 50% payload fraction.
Yes,
Okay?
yes,
You are able
that's
to
what
carry 600 to 1 kg in a UAV that weighs 1 to 1.5 kg.
So the thing is, in this design, what we came up with is, if we increase the speed of the UAV, it can carry up to 1 kg. So at the minimum 600, yes.
Okay, thank you.
All right. Saurabh Bagare, would you like to?
Yes, I have a few design related queries.
Yes,
Yeah.
sir.
Yeah. So, which aerofoil are you using?
We use Epler 3588 3375 Epler, that number we used for the
So it's a
airfoil.
cambered aerofoil, right?
Yes, it's not fully symmetric. Yes.
Yeah. So, how will you eliminate the backdrift that is caused by vertical takeoff of your aircraft? So, as you know, when your aircraft will fly vertically, the camber of the aerofoil will create a lift in the reverse direction, which will cause
Indeed,
the
sir.
backdrift of your aircraft.
Indeed, sir.
Yeah. So, how will you try to eliminate that?
Yes, sir. So that's where I mentioned that we will have a sliding mode. What do I say? So on the fuselage itself, there will be a sliding mode payload, not payload, like the components will be placed on a sliding mass kind of thing. And that sliding mass will change according to the drift. So for example, if it's trying to go back, the mode will go towards the front so that it tries to maintain the balance. That was the idea that we came up with.
Okay, so basically you are trying for a CG shift.
Yeah, CG shift. Yeah, because what we understood with the designs is that even if we have a symmetric, sudden gust of wind or a sudden tilt of the angle of the tilt wing will cause a huge moment shift. So we thought that even if we have this, and if you want modularity into structure, let's make a sliding CG shift kind of provision, so that even if the wing profiles changes, the inherent stability will still remain better than without having it.
Okay, and my second question is,
Yes, sir.
your forward rotor and your rear rotor.
Yes, sir.
The rear rotor will probably be affected because of the downwash of the forward rotor.
Definitely.
So, do you think this idea is feasible, or should you go for a different location of the rear rotor?
We checked that we have done literature review, and we found that yes, in some of the design, keeping the rear rotor a bit upward compared to, like, laterally upward compared to the front rotor, like the lateral positions, would be beneficial, definitely. However, we also found out that how about we have the different angle of attack. So front angle of attack has a different compared to rear angle of attack. So we wanted to even investigate that, because in some of the papers, we found that even if you change the angle of attack, independent, the front and the rear has a different angle of attack, the effect of downwash can be reduced. So this is what we found out. So to investigate further, of course, this is a prototype 1 version. We want to investigate further of this. Our possible options are to make the rear or motor up or have a different wing configuration. However, we also are afraid of the controllability. So that's why we thought of making the design simple and make a agile kind of development where we have one parameter fixed and then test it and again change it so that the controller also develops along with the configuration.
All right, all right. Appreciate your work. It will be great if you try to do a more in-depth analysis of internal testing, because we can't really know the entire performance just based on one wing. So it'll be better if you do it the tandem wing configuration into the internal testing as well in the future.
Thank you, sir, for your feedback. We'll definitely do this.
Yeah, that's it from my side.
Okay, thank you so much. Namanuddin, how are we on the time? Because even judges have to maintain the time of maximum 15 minutes.
Okay, okay. So, yes, you have time for 5 minutes more.
Oh, we have 5 minutes more. Okay. So there is one question which has come from the audience. There is one Dr. Rajesh Joshi in the audience who is a very accomplished aero modeler from Nagpur, and he has asked a question regarding the vertical stability during the transition from. So can you comment on that?
Regarding again the vertical stability during transition, sir, definitely these are the concerns that we also have. For example, the downwash and the wing coefficient of movement. So there will be just because the wing is present and this not fully symmetrical, there will be inherent coefficient of movement. So the stability during the transition, what we can say is while if there are two conditions, if there is no gust of wind, so we don't have any external condition, we do it in a very perfectly situated environment, then we definitely need the sliding mode of the CG shift in front and the, let's say, simple PID controller that tries to control the horizontal stability when the vertical takeoff is happening. Now, let's say there's a transition happening. So from this configuration to this configuration. So as this mechanism is trying to make the transition, there will be an counterbalance mechanism with the same servo motor, counterbalance that goes behind. So during the transition, the moment, the additional inherent moment that if we don't have a sliding mode mechanism, CG shift mechanism basically, the inherent moment had it to be done by the changing the at least the propeller or the angle of each of them. But since we have a sliding mode mechanism, this can be tuned along with the transition. So it is our hypothesis that because of introducing this inherent stability of the entire plane altogether, during transition, the counterbalance can help for additional balance. So our wings can focus only on agility and manuality rather than balancing it out. That's what we aim for.
Okay, there is another question from Wing Commander PK Sharma about the anti-torque mechanism during vertical takeoff.
Yes, sir.
What is your answer? Have you thought of any anti-torque mechanism? You have 4 rotors rotating.
Yes, yes.
How are you going to handle the anti-torque during vertical takeoff?
I mean, anti-torque in which direction, sir? The pitch or the yaw?
No, in a pure vertical motion.
Yes, yes, yes.
If I want to take off this aircraft absolutely vertically.
Yes, yes.
How are you going to handle the anti-torque from 4 rotors?
Usually the 4 rotors will be rotating at different RPM. So let's say RPM direction. So for example, this is anti-clock, and this will be clockwise. So that is just for the rotor effect. And if you want the wing effect to consider during the upward motion, we'll have the sliding mode balancer that can affect the wing. Have I cleared the doubt? Or
you have tried to answer this now. That's okay. See, if I can just comment, Nomanuddin, you have to give
time
us
up, sir.
Okay, the last question. See, basically, looking at your design and looking at the answers you are giving, it is
Yes,
very clear that you have not done any serious stability analysis of various modes. Okay, it's easy and
yes, sir.
simple to say that I will make or we will make a very complicated novel system, but at the same time, it's also very important to understand. And most of your answers are that we will do something to sort it out. For example, you're talking about sliding mode control, and you are thinking of putting a sliding mass. Now it's easier said than done, what you are saying. And also all your study has been only on a single, as the Saurabh Bagare pointed out rightly, all your studies, all your photographs, all your internal testing is on a single wing configuration. But the
Yes,
the speciality of your design is a double wing configuration with 4 rotors. So
yes,
you are still quite far away from realizing your concept, and the proof of the pudding is in the eating, as they say. So on paper, on a computer, on a diagram, you can show many things and you can claim many things and you can say that we will slide this, we will slide that. But in reality, the moment you bring in complexity, you have to be very much aware about its repercussions. And right in the beginning itself, you have to, for example,
yes, sir.
you have a coupled system which rotor also can rotate and also the wing can rotate.
Yes, yes,
Imagine the kind of complexity you are going to encounter. It's all right for a conceptual design, it's all right. Okay, I think we'll just move ahead now in the interest of time, but I must commend you on your attempt to go beyond the ordinary and to try out new configurations. So on that account, it's a good design, but it is far away from being established as a feasible concept.
yes,
It's
sir.
all right. We'll go ahead. Let's go ahead to the next team. The next team that I want to invite for making the presentation is the team Shivam Omni-Roll Electric UAV. So
Yes, sir.
yeah, so you can share your screen and you can start your presentation. So Namanuddin, please keep a watch on the time, both for the presenter as well as for the judges.
Okay, sir.
So the judges get 15 minutes and the 10 minutes actually, and the presenter gets 5 minutes. Yeah, so Shivam Bhandari is trying to share his screen. It's okay. Yeah, your screen is visible now, but you also make it in the full screen mode by clicking on, yes, on the bottom, there is a button for full screen. Can you make it full screen, please, Shivam? Oh, looks like we have lost him. Shivam, are you there? Can you hear us? Shivam, are you able to hear us?
Hello.
Yeah, Shivam, are you able to hear us?
Sir, this is Aniket, sir. I am his team member. I will
Okay.
present this presentation.
Okay, can you make it full screen?
Shivam, are you able to listen to sir?
No, if not, I'll do it. That is why I have copied your PPTs. So I think, Shivam, you stop sharing your screen. Shivam is requested to stop sharing his screen so that I can present it from my side. Okay, I am presenting it from my side. Just give me 1 minute. Right, so Aniket, you can start. When you say next, I'm going to go to the next screen.
Sir, I'm not able to see the presentation.
Your PPT is not visible.
Okay, my PPT is not visible. Okay, wait, I'll stop the share and I'll share it once again. Are you able to see it now?
Yes, sir.
Yes, sir. Yes, sir. Now it's
Okay,
visible.
so Aniket, when you start
Okay.
speaking, Namanuddin
Okay.
will start the timer, and I will click on the PPT when you say next. Go ahead.
Sir, I just want to ask that am I clearly audible?
Absolutely visible,
Okay.
audible, no problem.
Okay, sir.
Please start.
Yes. We all have seen the futuristic cities in a lot of movies where we have seen the small drones and UAVs flying among or above the huge skyscrapers. Even in some movies, there are shots which showcase a UAV chasing down fast moving vehicles, tracking down people, and shooting them down with a missile. This is kind of future for UAV we are looking forward to. Yes, today we are going to witness such one of a kind omni-role electric unmanned aerial vehicle. Good morning to one and all present here. I, Aniket Bateja, alongside my team, Galactic Eagles, welcome you all for this UAV Design Challenge presentation. Thanks to Aerospace Technical Society of prestigious Punjab Engineering College for giving us this opportunity to present our project in front of such an esteemed panel. Next slide.
Okay.
The introduction to Omni-Role Electric UAV. So this is a really futuristic design, goes out of the box as shown on the screen. It is powered by 6 high-torque motors, has no physical flying surfaces for roll, yaw, or pitch. That all would be done by the R6 gimbal motors. This UAV has a feature of converting itself into a drone from a conventional horizontal landing aircraft. This feature would allow it to vertically take off from rough patches and land without any airstrip. This combination is really effective for any agency to procure as it would be a cost-effective alternative showing showcasing its versatility and its futuristic design, which would be able to fulfill all the needs which would we have in the near future. Next slide. On your screen are the key components of our omni-role electric UAV, the special gear mechanism, the tilt rotor configuration motors, the new unconventional tail design, a highly resilient fuselage structure with a wing, and also a wing design which is able to withstand all the vibration and disturbances caused by the motor and the loads applied to it. Next slide. This is the internal aircraft structure in front of you all, made in a sense that it could withstand all the loads and the moments applied on it during transition, cruise, and landing. Next. Main questions asked on for this project are its capabilities to withstand the vibrations caused by the motors, as it is fitted with 4 motors on the wings and 2 on the empennage. So we have done the FEM analysis, the finite element. We have used the finite element method to showcase that it can withstand the loads applied to it. We have assumed a simple model of wing as a cantilever and have applied a point load on it for this first experiment. The second most challenge what we face is regarding the disturbance created by the first propeller during the time of cruise for the second one. We have used fluent analysis for it and have showcased different variations of fluid taking pressure as base. We have seen
4
that,
minutes are over, 1 minute is remaining.
yeah, thank you. We have seen that the disturbance is not a deal breaker for this project and we can work on it very easily. Next. Yeah, I have done this. Next. To conclude, I would like to say this omni-role electric UAV has a realm of possibilities to work upon. It gives us an ocean of opportunities in regards to versatility, and I believe this design is a cut above. Thank you.
Okay, thank you so much. Thank you so much for for maintaining the time.
Yes.
Let me now start first with Mr. Saurabh Bagare this time.
Hello. So how
Okay.
much time I
Hi.
have to count for judges?
10 minutes.
Okay, sir. Thank you.
So, Mr. Saurabh Bagare,
Yeah.
you can start.
Yeah. So as Professor Pant mentioned in the last project, it's very easy to say such concept, but when it comes to the math, it's extremely difficult. So for example, you said the testing of fans that you did in ANSYS Fluent, right?
Yes, sir.
Yeah. The configuration that you have tested for is like a ducted fan configuration. There is no interference between the two fans. But if you see your actual wing design, um, your front propeller and the rear propeller will interfere because of the wing that is between them. So claiming that this won't create any issues just because you have taken an ideal condition is a questionable thing to say when you're doing fluent analysis, especially for the aerodynamics of an aircraft.
Sir,
I cannot see any wing in between. It's just a ducted fan configuration.
sir, actually, yes, you are right, sir, that we have taken this ideal assumption. But the thing is that this concept is really in its experiment stages. And by what I meant that it won't be a deal breaker because we have gone through the literature and we have, and also from this testing, we have seen that yes, there would be some kind of interference, but it won't be much, sir. It won't be a deal breaker that it could not fly in that configuration.
Okay, another question is
Yes,
when
sir.
your aircraft is in a steady level flight, when the
Yes.
wing is closed, right? The two
Yes, sir.
wings are connected. So in
Connected.
a steady level flight, your wing will act like a symmetrical aerofoil, which means when your aircraft is flying in steady level, there will be no lift produced by your wing.
No, sir. Sir, I think, sir, no, sir, the lift would be produced because it is an, if you have seen, sir, it is an elliptical wing configuration. And as we all know that it has the highest efficiency and yes, sir, it will produce.
I'm not talking about the planform. I'm talking about the
Okay.
cross section.
The cross section. Sir,
The cross
no, sir.
section is symmetrical, right?
No, sir. We have used NACA 4412 airfoil and we have tested its limits to generate lift and we have got the desirable numbers.
If you have used NACA 4412, then you cannot mount a separate propeller on the front part and a separate propeller on the rear part, assuming that both of them are same.
So this is, I would be honest that we haven't considered this factor, but it's in testing phase. And I believe, sir, this issue would be resolved if it would be there.
And my last query is,
Yes.
you did such a good design, but you never talked about the three basic control axis of the aircraft. Pitch your role. How will your aircraft execute
Sir,
pitch your role?
yes, sir. Sir, I in the starting only I said in the introduction part that there are 6 gimbal high torque motors and there are no flying surfaces. So we would make an integrated computer system which would allow the motors to gimbal in a manner that they could pitch, roll, and roll.
So if you are pitching, yawing, and rolling only based on your motors, then there is essentially no difference between this design and a quadcopter, to be honest. The aerodynamic advantages that you want for aircraft are not seen if you are controlling the entire aircraft using 6 motors. I cannot see any aileron, I cannot see any elevator, I cannot see any rudder.
Sir, but we have fixed like 2 motors at the empennage, and we have gone through the literature, and we have also seen that what it can do. And sir, we don't think that it would give it as it would be a disadvantage because there are no flying surfaces. I believe that it could perform better than the conventional one.
You may try it, but yeah, anyways, best of luck, and I hope
Thank
you
you, sir.
study more on this design.
Yeah, sure, sir. Thanks for the feedback.
So, Deepak Lekhiji, over to you now.
I have just 2 doubts.
Okay.
Number one is when you confidently said that vibrations will be taken care by the wing. In fact, so what is that giving you confidence? What type of simulation you have done for that?
Yes, sir. Sir, as I mentioned while I was speaking for the design verification, that for this first phase of experiment, we have just assumed a simple model of wing being an cantilever and a point load applied. As you can see, the red color, the load is applied there. But we got, sir, some unexpected results. We got better results than we thought, and I believe that this wing can withstand the other if we'll apply some kind of UDL or UVL on it, and the vibrations can also be managed easily.
No, one is putting the load and seeing the stress or strain on that particular member.
Yes,
Have
sir.
you done the vibration part, which is more dynamic? You are talking of static analysis now.
Yeah, yes, sir. Sir, that's what I'm saying, sir. That we have gone through the literature, but that particular vibration part we haven't tested yet. But it's in the phase of testing, and it would be done soon. But from the literature, that's what my point is. But that from the literature, we are confident that vibrations would not be a big deal to handle, sir.
And second question is, have you realized any hardware till now, or everything is in this thing design?
No, no, sir. No, no, sir. Sir, for the prototype, actually, we were about to order everything, and we were on the last phase of getting funding from our college. We were about to get that, but the imports from the China got banned, and now we are. That's not a major issue. Now we are finding some another place to get our components, and we have a list of components to get our prototype in real life. If it would have not been of this coronavirus pandemic, by now our prototype would have been flying.
Okay, thank you.
Yes, sir.
Okay, I have a question on the slide that you can see right now on the FEM analysis.
Okay.
If you look at the figure of stress analysis and strain analysis.
Yes, sir.
The colors are absolutely identical. Okay, but
yes,
the scales are different. Okay, so
yes,
can
sir.
you please explain to me what is
Yeah,
happening so that both of them are having exactly the same color scheme?
Yeah, we have, sir, a specialist about this. Shivam, are you able to listen to sir? Hello? Shivam?
Hello, sir.
Yes.
So actually, we have done stress and strain analysis based on the different type of load acting on a cantilever beam. So, sir, first of all, we have applied the load on the wing tip of the wing.
No, 1 minute.
So,
1 minute. That is one. No, wait. So let me first ask you that. What is the basis of assuming that there will be a tip load in this kind of configuration?
Sir, actually, we were just only in a trying phase, and we were only trying to get the values in cantilever beam with using a point load.
No, but tell me the logic now. Why are you assuming that there is a tip load acting on a wing like this when you have mounted a motor
yes, sir.
in the center?
Yes, sir.
What is the logic of assuming that just let us apply some tip load?
Sir,
how much
actually,
did you, what is
we
the tip
were,
load how much load did you apply in the tip?
Sir, 2000 Newton.
What is the basis?
So actually, we were just trying to get result and how this wing will.
No, come on. How do you decide at a number of 2000 Newton? Why not 250? Why not 10,000? And why do you apply a tip load? I mean, what is the logic of having a tip load for a wing like this?
Sir, I want to do a bearing load also, but due to the constraints of my computer, I could not do such analysis because
Come
it
on,
took
now don't give me that. I'm sorry. I cannot buy that argument. I cannot. Are you saying that your computer allows only tip load analysis?
No, sir.
Sir, I guess the logic behind it that sir, my fellow mate is not able to justify it.
No, you said he's an expert. Now wait a minute. You said he's an expert.
Yes, sir. He does
then what
this
happened?
all.
Then why are you answering when he's an expert and when he has done the analysis? Okay. You just don't answer. Let him answer.
Okay, sir.
This is a team effort. Okay. See, understand, friends. If you don't know the answer, you say I don't know the answer because you are digging a deeper well. By trying to give misleading answers, you are just putting yourself in a deeper situation. The two figures, stress analysis, strain analysis, are absolutely identical. They are like a photocopy of each other. Only change I see is in the numerical values. And let me ask you the question about deformation. You see a deformation of 600.25. Is that millimeters?
Yes, sir. Yes, sir.
So under a load of 2000 newtons, this wing is deflecting 600 mm. And you are saying that you can take care of vibration loads.
So actually, sir, we were trying to do, and sir, it is in a testing phase, and in future we will.
Then why are you presenting your results? If the results are not final, if they are not at all, then why are you presenting them as if you have done some great analysis? I'm sorry, this is not, you are trying to mislead the judges in trying to show some colorful pictures and assuming that we will get impressed by the colorful pictures, but we look at the numbers. Look at the numbers that you have got.
Yes, sir.
Okay. Look at the numbers that you have got. Look at the pressure in the propeller that you have got. It's 3,425. What are the units?
Sir, sorry for interruption. Time up for this.
Okay. Thank you so much. Thank you, Namaruddin. We can go on.
Thank you, sir.
I would like to now request. Okay, there was a question from Sunny Kumar, but there is no time for it. Sorry, Sunny. We'll now go to the next team, which is Saurav UAV Design Challenge. Saurav?
Am I audible?
Yes, you're audible. You can now share your screen. I have allowed people to share the screen, so you can share your screen.
I would request Anand Mohan Singh and Priyanshi Jain to also check their mics.
So are we audible?
Yes.
Priyanshi?
Yes, sir. Am I audible?
Yeah, but Priyanshi, there is the echo from your side.
Is the screen visible, sir?
So the moment you, the screen is visible. The moment you start speaking, we are going to start timing you. Okay.
Okay.
Fine, sir. I'm ready to begin.
Okay.
All right. Good morning, everyone. I'm Saurav Alawat at Team UASDTU. This is our UAV Design Challenge submission on Tilt Tricopter VTOL. Our presentation will go through the design approach of the mission objective, from conceptualizing the design to preliminary and detailed design phases, concluding with the flight software used. Anand Mohan Singh and Priyanshi Jain will join me in presenting, where we will achieve the mission objectives of delivering our payload on an unconventional design.
Exhaustive research was carried out and different configurations were studied. Keeping the idea of unconventional design in mind, a plane with vertical takeoff and landing is selected. Out of various possible configurations, tricopter configuration was selected considering the parameters of weight, airworthiness, and stability. To enhance the lifting characteristics of our aircraft, blended wing body configuration was selected, which is more aerodynamically efficient. For wing designing, various airfoils were analyzed on XFR5 software by considering the control parameters like pitching moment and lift coefficient. From the analysis, MH60 airfoil was selected as it has the highest design index. Following wing analysis, fuselage airfoil was also analyzed on the same software. NACA 25112 was selected owing to its self-stabilizing characteristics.
A brief market review of available materials and manufacturing trends in UAV design led us to choose the highly favorable composite structure with its light and robust framework. Further, the carbon fiber composite was distributed according to various available densities and fiber arrangement types over spars, ribs, and various skins of the body.
All three axes of stability was investigated on XFR5 software by maximizing damping factors of Dutch roll mode and Fagoid mode. The aircraft design was reiterated until a desirable value of static margin was obtained. Further, wing parameters were optimized using genetic algorithm by giving us certain variables and constants. Input parameters like random population converge to an optimum solution until net fitness of the generation reaches a maximum saturation point. CFD analysis of aircraft was performed at every design stage to obtain the best aerodynamic features by maximizing lift by drag ratio.
Structural analysis on key design points like the motor boom and wing was conducted, and results were obtained on abacus by various iteration of loads. An algorithm which refines our wing geometry underwent steps of estimation of load, division of sections, to the calculation of moments of inertia on each of these paths to determine its final geometry. An important aspect of maximizing the endurance was propulsion selection, where we arrived at an all-electric solution owing to its ease of operations and overall efficiency in design. The electric drivetrain was further analyzed and optimized, with the final configuration of motor and propeller was selected for both hover and cruise specific motors. A special consideration was given to designing and perfecting the tilt mechanism and its modus operandi of an unstable design governed by the autopilot cycling between both the hover and cruise segments of the flight.
PEC Cube is our flight controller, which control actuators like servo motors and BLDC motors through S using the sensor data from various sensors such as airspeed sensor, GPS, and Intel RealSense. A ground control link is maintaining communication with the tricopter through telemetry, and a RC link is used by the safety pilot for manual control. The control architecture consists of navigation, position, and attitude control loops. The mixture takes position and attitude data to control the actuators, which drive the
4 minutes
VTOL
are
engine.
over. 1 minute is remaining.
Thank you. The sensors, with the help of estimators, provides position and attitude feedback to the previous loops.
That would be all. Thank you.
Okay. Lekhi ji, shall we start with you?
Yes, sir. Sir, my first question is this three propeller scheme what you have used.
Yes, sir.
All the three propellers are having the same power for the motor power?
No, sir. The forward motors are actually half the thrust of the rear motor.
Okay.
Basically, the center of gravity is placed on the midpoint of the y-axis in the direction of motion.
Okay.
The rear motor has twice the propulsive power of the forward ones. Basically, we iterated various motor configurations on how we could optimize our cruise endurance. The forward motors are pinpoint designed for cruise efficiency. Like when they'll operate at their pitch speed of 25 meters per second, the UAV will be flying at a 25 meters per second. And the thrust produced will be equal to the drag of the aircraft. And the remaining thrust during hover phases will be handled by the rear motor and the front motors together.
And you are only tilting the front propellers, not the rear one.
Yes, sir, we are only tilting the forward ones.
Okay, reason for that?
Reason for that is we have sufficient thrust from the forward motors to complete all segments of our flight. The forward motors have a maximum T by W of 0.8, which is enough for any normal maneuvers in the cruise condition.
And what is your payload section?
Okay. Our payload is 750 grams and our total all-of weight is 7 kgs. This is for maximizing our endurance for 81 minutes. We can swap the battery packs for higher amounts of payload, but that will cost the endurance.
So it's like 10% of it is
it is 750 grams
is allocated for the payload.
Yes, sir.
10% is allocated for the payload.
Yes, sir. It is for the maximum endurance capabilities. We can reduce our batteries up to say the frame's weight is 3 kgs sans the batteries.
Or if you compromise on the endurance, then what is the maximum payload you can take percentage-wise?
Yes, sir. Our plane's weight is 3 kgs and the remaining 3.5 kgs is for the batteries, and the rest is allocated for the payload, so that our all of weight is 7 kgs. So we can reduce our batteries to half a kg. We can have a 6S1B configuration which can fly for 10 minutes but carry a payload of 3 kgs.
Okay, thank you.
Yes, sir.
Saurabh, you want to go ahead?
Yes. So can you show me your fuselage photo?
Fuselage photograph. Okay, sir.
Yeah, the top view of fuselage. Top view of fuselage as you shown in the presentation. Yeah. Can you justify this diagram? I'm not able to comprehend what this diagram is.
This diagram shows the top view of the fuselage and not the cross section of the airfoil as discussed on the slide.
But top view of the aircraft fuselage should be a wing, right?
Top view of the fuselage is a blended body design. So this
Yeah, so it should be the blended wing. Why am I seeing some unsymmetrical diagram here?
This is the half of the body in the center. It is without the wings. Basically, this is to analyze how we can place the components inside the body and how we can shape the body to a perfect blend without any
All
interfering.
right, so it's a half diagram. Cool.
It's a
Yeah.
half diagram.
My next question is, how will your aircraft turn?
Turn as in multi-rotor mode or a fixed wing mode?
Do we care about that? We just want an aircraft to turn in any way possible. If you are
Okay,
flying
so
and
in
you
the
want it to turn,
multi-rotor
that's it.
mode, we are operating in a tricopter configuration. A tricopter is inherently stable with its vector yaw mechanism. So when it's hovering, it can act as a normal multi-rotor. It can do its
No,
role.
I meant a steady level turn. Steady
Yes.
level turn.
In a steady level flight, we have our ailerons. We fly as a normal blended wing configuration. We have Skywalker X8 models available in the market.
Yeah,
Skywalker.
yeah. So
We have ailerons. Yes,
yeah.
sir.
So my main query is, you will turn using the aileron coupled motion, right?
Yes, sir.
Yeah. So because of that aileron coupled motion, you will have a roll moment that will cause your propeller at the rear to cause a drift that will change the altitude of the aircraft.
The rear motor is not operational on the cruise segments of the flight. It shuts down during transition.
Okay. So it shuts down whenever your aircraft is flying in a steady level.
Yes, the forward rotors will tilt forward and it will act purely as a fixed wing during the cruise conditions.
Okay. Then my next question is, in your graph, in your comparison that you have shown with your configuration with other configurations. Yeah, this is a diagram.
Yes.
So based on the values that you have put, I can see that you have assumed your design to be better and put the values accordingly in the table just to show that your design is better.
No, sir. The fact that we assume our design is better is based on these facts, on the market research that we
No.
conducted.
What I'm saying is the distribution of marks that you have and the weightage of the things that you have shown in this table.
Yes,
for us, it seems like you have assumed that your design is already, like, you're already biased to your triplane design and given points such that it scores higher than the others.
On the contrary, sir, the market research we did concluded in such a way that we should choose a tricopter for a long endurance mission. All other configuration would have scored better if it would have been a payload
Then you
specific
should have
mission or a specific
referred to the survey that you have done, because when I see the values in this particular table, I can clearly see that you are biased towards the triplane configuration, and you have this table just to show that it is better.
Is there any specific point in this table which you think is contradicting to your?
No, what I mean is, like, the distribution of marks, like 4,
Yes,
3, 2, 3, it's very relative in nature.
Yes, sir.
So when you do it, you have to have some kind of a ground-based benchmark system to compare all of them. But I cannot see any benchmark system. So now when I see you rated maybe ease of fabrication 3 for your plane and a triplane with tilt motors 2, I get to know that you put 3 for your plane just because you feel it's easy to manufacture for you.
Yes, sir. Like a triplane with 2 forward tilting motors is easier to fabricate than a triplane with all tilting motors, as it will have a servo in the back and a robust
Yeah, so
structure
there should be some kind of a benchmarking parameter that should define to keep the comparison uniform throughout.
Okay,
that's
sir.
what I want to know. Okay, and my last question is to your control systems person.
Yes, sir.
You're using PECSOC, right?
Yes, sir. We are using PECSOC.
PECSOC has no dedicated mode for your configuration.
It has, sir. It has
it has a dedicated mode for blending wing, and it has a dedicated wing for tricopter.
No, sir. When you are operating on a ADU plane configuration, you can enable your Q tilt mass to 7, which is a tricopter.
So you have coupled them.
Yes, so we have actually tried to simulate it on what do you call that? The SITL software, and we are already working on developing this concept.
Okay, but I believe you will need your own code, but that's left for the future. Then that's it from my side. Yeah.
Yes.
Yeah, okay. So I only have one comment. And if I look at the constraints specified in the document which was given as the brochure, there is a clear mention that no fixed wing aircraft qualifies for the competition. So you have designed a fixed wing aircraft, but as per the problem statement, a fixed wing aircraft is not feasible.
So this is a VTOL concept, like
It may be, but it is a
has
fixed
all
wing
the
aircraft.
advantages of
No, it is a fixed wing aircraft.
Understood, sir.
And the document clearly says that fixed wing aircraft is not feasible.
So, but like all our design was towards optimizing the VTOL. Even the fixed wing sizing was done so that during the transition phase from multi-rotor to
No, whatever you may say, but the
highest.
constraint clearly mentions that no fixed wing design will be feasible. Have you read the document carefully?
Yes, sir.
So then why did you design something which is fixed wing when it says very clearly that fixed wing design is not feasible?
I believe that the VTOL qualifies for an unconventional design, so we went
No, this is not a VTOL design competition. This is a design competition where there is a constraint clearly mentioning, it is given in bold, constraints, no fixed wing design, no fixed wing aircraft / quadcopter / conventional design qualifies for the competition. Then why have you gone for a fixed wing design?
I cannot justify more than what I just said. Like, believe that the VTOL was an unconventional design and it did not qualify purely as a fixed wing. That's why.
Anyway, I have made my point clear to you because this has been raised by somebody in the audience very rightly, saying that this particular design does not qualify simply because it is not meeting the constraint. If you have an answer, then we can take it. If you don't have an answer, then unfortunately, we will have to disqualify purely because of the problem statement.
So this is not a purely as a fixed wing design. Like
you may
having
add so many things.
Yes,
you may add so many things to a fixed wing. Okay, you may add things to the fixed wing, but if it is basically a fixed wing, then it is a fixed wing, isn't it?
So, but it has more advantages than a fixed wing. You cannot qualify a VTOL purely as a fixed wing. It has the ability to.
Okay, I'll leave it to the judges.
use of
Don't worry, I'll leave it to the judges. Okay, there can be difference of opinion. I have no questions. I mean, you have made so many claims in your design. We don't even have time to go through all of them. For example, you are going for a single spar structure on a wing, which is going to be a fixed wing. I have my doubts whether a single spar structure, especially in the outboard section, right from the mid-span, you have a single spar. How are you going to take care of the torsion? Tell me.
So we have two layers of carbon fiber which is wrapping the wing, and we're pretty sure that with that layer we'll have a structural integrity.
Are you saying that a single spar wing?
So we have actually fabricated such a.
Let me complete my question. Are you saying that a single spar wing from mid-span can be made torsionally stable just by putting a carbon fiber skin over it?
Yes, so we'll also have
no discussion. No discussion. Thank you so much. If you are sure,
I want to add one last point. Like we have already.
I'm asking you a very standard technical question. You have to say yes or no.
Yes, sir. It will have torsion in it. It will rotate, but it is under our design limits, and we have already manufactured such designs in our laboratory, and we have already flown them.
Sorry for interruption. Time is up.
Okay, thank you so much. Time is up. We'll go to the next one. Stop sharing your screen, please. We will now invite Lokesh Bansal to make the presentation. Lokesh Bansal, UDC.
Am I audible, sir?
Yes.
Yes, sir. Should I start?
Yeah, you can start.
Is it visible? Yes, sir. So good morning, everyone. The topic of my design is autonomous, inherently stable, high stealth airborne platform. Now, coming on to the stealth aspect of the design, So the outer body is having diamond-shaped sharp projections. So these projections will reflect away the radar waves from the source of radar signals. In addition to this, the surface is coated with radar absorbent material to provide extra stealth. Further, in the UAV, there is no heat emitting source. Hence, no heat sensing device can detect the UAV. Furthermore, the two counter-rotating propellers are inside the casing that result very less noise in comparison to conventional configurations. Furthermore, the color of UAV is grayish dark, which result in poor visibility of UAV, especially in evening or night times. Now talking about the working and stability. Talking about the stability of the UAV, for vertical stability, it is inherently stable because the CG lies below the center line. Then the two counter-rotating propellers provide yaw stability. Now coming on working. For thrust, the two rotors will throw the air through the four nozzles at the bottom surface and create thrust. Then for flight directions, we are controlling the direction by thrust vectoring. It can be done by following three methods. Like you can see, there are method 1, method 2, and method 3. In method 1, the nozzle is divided in horizontal and vertical directions. Then the flow is divided between these two nozzles to get the desired force components. In method 2, the complete nozzle is getting tilted in our desired force directions. And in method 3, we are controlling the exit area of four nozzles to divide the thrust to control the thrust output. So we can use any of the method for the thrust vectoring. These are very simple, and we are controlling the system using a servo motor and a flapper. Now coming on to the flying aspects. Very fundamentally, we can fly it using remote control. Further, we can easily make it partially autonomous, that will be able to fly with the help of GPS connectivity using mission planner software. Using the software, we can easily set the flight trajectory of the UAV. In addition to this, the UAV is capable to detect and track our target with the help of image processing applications. As you can see, the preliminary result of image processing of target recognition, detection, and tracking of helideck on ship, which is assumed to be our target. These are results of tracking of the target. A platform is moving from one end to another end in the video, and after video processing, in 80% efficiency, the code is detecting the target. Of course, there are some outliers also, but these can be removed using particle or Kalman filters. These are only preliminary results. So the UAV is able to recognize the environment as well, then detect exactly the center point of the target and track it as well. So this is the flying and tracking of the target. Now coming on to the applications of the design. So it is very easy to make, easy to fly. It is very low cost. No bigger things are involved in the design. Only the PEC processor, Raspberry Pi.
4 minutes are over. 1 minute is remaining.
Yeah, thank you very much. So further, it can be launched by ejection from manned aerial vehicle or long range UAV in target range proximity. Then it can be automatically carry forwarded with the help of GPS navigation, or it can be controlled from ground station or any other controlling platform. Thank you very much.
Okay, so let us start with Saurabh Bagare.
Yeah. Okay. So Lokesh.
Yes, sir.
Yeah. So you told me that your propulsion system consists of nozzles, right?
Yes, sir.
Have you done any analysis on the choking parameters of the nozzle?
No, sir. Choking analysis has not been done, but I assume that the choking should not be there. Like the nozzle have sufficient area. The
No, what do you mean by sufficient? See, if your propeller rotates at some RPM, it
Yes,
is
sir.
producing some thrust, and then that air goes into your nozzle. So how can you guarantee that the dynamic pressure that the air is applying on the throat of the nozzle is less than the ambient pressure of the air around it? If it is less, then the nozzle will be choked,
I
whatever
understand.
may be the area.
Sir, that is one calibration and design aspect that can be rectified during design. I assume that is a rectifiable problem, sir.
No, how will you rectify it then? Because you are constrained by the size of propeller.
No, sir. Size of propeller is RPM is low, sir. The RPM is low. We are taking low RPM and more diameter of the propeller.
Yeah, so there has to be some kind of a study done to compare all of these parameters. You cannot just claim that this design can fly and it will fly. Because it has nozzles, it makes it really difficult to fly, to be honest.
Yes, sir. I understand the concern.
And my next thing is you claimed quite a few things about the stealth capabilities of your aircraft.
Yes, sir.
So can you tell me the factors on which stealth parameter radar signature of an aircraft depends on?
So, sir, it should not detected by the radar, basically.
No, that's what. What are the things that influence that? That's what I'm asking. What are the parameters? How can you decide that this body is not detected by radar and this body is detected by radar?
So, sir, if the radar is sending a signal and it is getting reflected by the UAV and the radar is able to catch the signals back, then it can be easily detected by the radar. But
That's what I'm saying. So what parameters have you put in this particular design that you say that it is difficult for radar
yes,
to observe?
yes, sir, I'm coming to that. So you can see the outer body have these diamond-shaped projections throughout the surface.
Yeah.
And these will throw away the radar signals from the source of the signal.
Okay. So now
Yes.
I'll tell you that this diamond-shaped design are uniform throughout the cylinder. That
Yes,
makes it a regular figure. And any regular figure is easily detectable by radar, even if you paint it green. The moment you said that you have equally spaced, equally sized diamonds on your outer cylinder, it will be detectable by radar.
Okay, sir. So
the very fact that an aircraft becomes stealth is because it has irregularly shaped angles. And what you have done is just painted gray, but put all the regular uh, diamonds all over the body. Even if the signal gets reflected in a different direction, the radar will be able to catch it. It will have a good radar signature.
got it,
So
sir.
you cannot claim something as stealth just because it is painted gray and has a radar absorbing material. And again, you have just put one set of counter-rotating propellers that cannot take care of its maneuverability. It cannot maneuver anywhere you want it to go. It will just have a single direction of motion. It cannot have multiple degrees of freedom.
Sir, by controlling the nozzle areas and nozzle thrust vectors, we can tilt the system and we can fly in a desired direction.
That's the thing. Now you're talking about nozzle again. But in the first part only we said that talking about nozzle without doing calculation puts you in a questionable position.
Yes, sir. I understand.
So yeah, that's it.
Okay, Lekhiji, would you like to continue?
Yes, sir. I have continuing with the same point of radar signature. Actually, what I feel it is overkill. You have done shape, the diamond shape, the radar absorbing material, no heat emission, and it is ducted. So, what is the size of this UAV?
Sir, so, sorry to interrupt, sir. Your voice is very low, sir.
What is the size of this UAV?
I'll repeat the question. What is the size of the UAV?
Sir, its radius is 22 centimeter.
22 centimeter.
Yeah.
Because
yes.
I feel this itself is a very small size. and you are putting so many factors, multiple factors for the radar vision. But do you think it is overkill?
Sorry, sir, your question is not clear.
Yeah,
Sir.
it's anyway a very small size, Lokesh. So that's why he's saying that if it is such a small UAV, then do you really need to bother about so much of radar signature, etc.?
Yes, sir. Like your point is valid. Like although the size of the system is small, then but still, sir, if the zone is very highly sensitive, then this will help, sir. Certainly, it will help.
No, the question is, it is such a small UAV anyway. Even its dimension is so small, there is hardly any signature just because of the size. On top of that, you are putting so much of effort and explaining your one slide is dedicated to diamond shape and RAM and heat emission, etc. Let's move on. Next question.
Yes.
Next point is, where are you going to plan to put your payloads if everything is ducted?
Yes, sir. Payload is here, sir. You can see at the bottom of the hub, sir.
No, but do you think its field of view is restricted very much? Field of view of payload, is it a deliverable or it is a capturing thing?
Sir, your voice is breaking, sir.
This
Yeah, so I
payload
will
is
repeat.
delivered.
I will repeat the question. So his question is that you are putting the payload in the hub in the center.
Yes,
it
sir.
will have a very small field of view. Okay, its field of view will be very small because it is mounted at center on the bottom. So it's going to look only at a limited area.
Yes,
Just
sir. It
vertically
will
below.
go.
No, see, it is mounted inside because your whole thing is enclosed inside the body. So I think only the lens of the camera is going to be pointing outward. So it will have a very limited field of view. Okay, the other question is that, Acha Lekhi ji, any more questions you have?
That's it, sir. Thank you.
Okay, so there is a question to you, Lokesh, about how you are making such a rough non-aerodynamic body to fly. And also, what kind of cruise velocity are you expecting? What is the speed you are expecting, Lokesh, from this design? Lokesh, are you able to hear us? Lokesh, if you're not able to hear, then maybe you should answer your question via the chat window. What is the cruise velocity and how are you going to make such a rough non-aerodynamic body to fly? And also there is a question about the thrusters in the bottom, CG above that. So this is going to be inherently stable. So how are you going to manage that? Okay, looks like we have lost Lokesh on the audio. We are not able to hear. I'm not even sure whether he is able to hear. Let me see if I can. Let me see if I can send him a direct message. Okay, looks like we have. So, Namanuddin, are you able to hear me?
Yes, sir.
Okay. I think we'll have to move to the next.
Hello.
Lokesh, good. Nice to have you back. So,
Okay, sorry,
Lokesh,
sir.
could you hear the question, Lokesh?
Yes, sir.
What is your answer? Because we don't have time. This is the last question. Shall I repeat the question for you?
Yes, sir. Please, sir. Repeat, sir.
Okay. The question is that this is a rough non-aerodynamic body. How do you make it fly?
Yes, sir. Sir, the speed will be low, sir. It's not our design aspect of the speed. So it have to be ejected in the range proximity, sir. It will go slowly and it will plug off the payload on the target, sir. It will.
Okay.
It have to be ejected from the man aerial vehicle or long range UAV in the target range proximity.
No, you also said that it can be controlled from a ground station. Anyway, you're also the thrusters are at the bottom, so the CG is above that, and that is going to be inherently unstable. How will you manage that? In the cross section, if you go to slide number 3, we
Yes,
see
sir.
that the thruster is in the bottom, and payload, battery, motor is above that. Okay, so how is it going to be stable?
Sir, vertical stability, I think, should be there. The
The
thruster
time
should.
is up.
Okay,
Hello.
time is up. So we'll go on now. Now we are left with only one team, that is Team Maverick. Okay, so Team Maverick Skywalker, you are welcome now to share your screen and make your presentation.
Yes, sir. Sir, is my screen visible?
Yeah, make it full screen. Right, it is visible.
So can I start?
Yeah, you can start. Namanuddin, please note when he starts, you have to start the timer. Okay, go ahead.
Good morning, respectable judges. My name is Karan, and on behalf of Team Maverick, today I'm going to deliver the presentation on our UAV design titled as Skywalker. Coming to the design methodology. Uh, our team has basically 3 domains: structures, aerodynamic, and propulsion. The work process of each domain are interlinked with each other as shown in the flowchart. In the middle, it is a working of an aero domain that involves the sizing, calculation, and simulation. On the left is the structures where we make the CAD model based upon the calculated sizing and select the material. Simultaneously, there's a propulsion domain towards the right where they work simultaneously to select the most appropriate electronic components. So starting with the aerodynamics, we have explored 3 different aircraft configurations, and we have defined certain factors that actually affect our configuration. And from there, we found out that Rogallo wing configuration is the most favorable for our design. So once we have selected the configuration, we wanted to design an aircraft which is not only just lightweight, but with a higher endurance. So we plotted our wing loading versus power to weight graph, and we found out our design constraint. And from there, we actually calculated our wing loading and estimated weight. After performing all the aircraft calculations, here is what we made the CAD model and are the dimensions of the aircraft, wing, and empennage. Uh, just like performing calculations, we have also calculated the drag of each component through empirical formulas, and we have validated the value through a 3D drag analysis, which we performed on our Autodesk flow design software. We've also performed the wing simulation in ANSYS CFD Fluent 19.1, where we obtained the pressure and velocity contours. Coming to the material selection, now once we're done with the aerodynamic calculation and CAD modeling, we started selecting the material. First of all, we explored the different materials which are available in the domestic market, materials that we can possibly use for our design. And now once we got the list of material, we have applied the material on, for example, if you consider the fuselage, we have applied different materials and we have applied the load, and we performed the static structure analysis, and we found out the material which is showing the least deflection. And from there, we concluded that the carbon fiber was showing less deflection, so it was selected. So following this same methodology, we have selected the material for other components of our aircraft. Coming to the propulsion system, based upon our previous experiences and based upon the practical testing, and based upon the estimated weight, we have calculated the required thrust. And with that thrust, we have calculated, using that, we actually explored the different configurations of motor and propeller that could provide the satisfy the required thrust. And we have plotted the graph, and we found out that the Scorpion 1122 motor, along when used with a propeller 9x6, was giving a better performance, keeping in mind that we have to maintain a smallest and lightest weight as possible. Here are the entire specification of the propulsion system, and some of the highlighting features of our design, where it has an empty weight of 0.473. It has a reliable hand launch, and it has a secure payload bay, and it has a high endurance capacity. And one of the most important features was it is portable with foldable wing, so it can be put inside any tube and it can be carried anywhere. That's all.
Okay, thank you so much for your presentation. Saurav, let us start with you.
Yeah. So I appreciate that you considered Rogallo wing as a configuration, but I would like to point out that there are some fundamental flaws with your design.
Yes, sir.
Yeah. So first of all, you did your test in ANSI static structural for a wing that is made up of fiber.
No, sir. It is the wing is not wing is made up of fabric. The fuselage is made up of carbon fiber.
Sorry, fabric. So for a cloth material wing, you are doing static structural.
No.
Can
So
you show your
static
FEM
structural
analysis?
was
Yeah, show your FEM analysis above, one above.
So
one above, slide number 6.
So this is wing simulation.
Okay, go.
Yes, but wing is cloth, right?
Yes, sir.
How can you do static structural on a cloth?
Sir, this is a CFD.
Yeah, so you have to do dynamic CFD for a cloth. That's how it
Yes,
works.
sir. Actually, yes, sir. I totally agree with you. But the things like actually we didn't know that we had to use different CFD for this one.
Okay, good that you realize. But my next point is Rogallo wing has to be maneuvered by controlling the fabric of the wing. But you have put a separate empennage. And that's one big flaw because whenever there is crosswind, your wing will catch it.
Yes, sir. So actually, during doing the literature survey, so we found out that in 1950s, the NASA was studying the hand launch vehicles, and there they were performing the experiments on this design. But there they had some issues, and their design was unpowered one. So for our case, we designed a powered UAV, but there are still certain issues there related to the stability.
See,
So we decided to
is
use.
Yeah, that is all valid, but you're not getting my point. That historically, Rogallo wing has been controlled like a parachute. You pull and push the fabric of the wing. But in your case, I cannot see any control or any motor that can control the fabric of the wing. And that puts it at a very difficult position to counter crosswinds. Because if there is some crosswind, there is nothing to pull the wing in the direction opposite of the crosswind. And since your wing area is very high compared to your entire aircraft, it is very difficult to counter any type of crosswind. Your aircraft will just drift away with crosswind unless you pull the wing.
Yes, sir. And the thing is, sir, this aircraft was designed for a very low speed. So when we actually doing the literature survey, so we also come across that one paper where they told and they justified it that if you're using any powered engine like powered electric motor over there, so the amount of if you keep amount of thrust sufficiently high, maybe the facts what you have mentioned can be actually overcome.
Yeah, so you need to put that in the PPT to prove the points because regular wing is a very questionable configuration when it comes to crosswind stability.
Yes, sir. Actually, sir, in the report I have mentioned, but we, as Rajkumar sir has asked to reduce the number of slides, so we decided to stick with what we can show and what to not show. And here
no, but you can answer the question, na? You cannot hide away.
Yes, sir. Yes, sir. Yes,
you
sir.
answer the
Yes,
question.
sir.
And another thing is, I cannot see any structural frame that is guarding the fabric wing. I can only see the T frame.
Sir, can you please repeat your question?
Like, how will you guard the wing? Like, you have to mount the wing such that basically the fabric such that it won't fly away, right?
Yes, sir.
So how are you sealing the fabric on the outer frame of the particular triangle,
Sir,
basically?
yes,
Can you zoom
for
into
that
the
also we
triangle?
found out. Wait, sir.
Yeah.
Yes, sir. And yes, sir, that is also one of the issue that was faced previously. So if you know that there is a one material that is used in stitching cloths, like if you see the collars, they use that material that I don't know this name, but it is kind of thing that makes the structure stiff. So when you're using the fabric, we thought that maybe if we could use that same material in between the fabrics of the wing, maybe we can make our wing, just like what it is showing in the CAD model.
Okay. And my last question is, why have you gone with a VTEL configuration?
Okay, so I'll go forward and answer this, Karan. So we majorly went for VTail because firstly, our structure itself is very lightweight. So if we go for a tail, we have to make sure that it would be lightweight as well to withstand at the same time. Secondly, it also has lesser drag as compared to other configurations.
Yeah, but I cannot see any flaperons or anything on the, sorry, rudders on the tail, rudder elevator.
There are ruddervators, sir.
Okay, there are ruddervators. I cannot see in
Yeah,
CAD,
yes,
that's
sir.
why I asked.
Sir, there are ruddervators.
Okay, cool. Yeah, thank you.
Thank you, sir.
Lekhi ji, any questions you have?
On the same slide, this slide number 7, what you are showing, actually, you have talked of packaging efficiency of 5, something like that.
Sir, your voice is breaking.
You have talked of some packaging efficiency of 5 in your design.
Yes, sir. Yes, sir. I have mentioned somewhere like here, packaging efficiency.
Correct. And
So,
when you see the
yeah.
number 7,
Yeah, now go to slide number 7 now. Go to slide number 7.
Now we go to slide number 7.
And make it full screen, please.
When I see your fuselage,
Mhm.
in the center you are using payload, correct? That is a payload window.
There is
Yes,
a
sir.
payload bay in the center.
Correct.
Yes, sir.
So, but if you see this fuselage, you are not even using 50% of the space.
Yes, sir. The reason being because first of all, we wanted to stick with the competition constraint that was provided, and secondly, we could have used more space. I totally agree with that, uh, but we also wanted to use as much less material as possible.
No, his
So-
question is that your fuselage is having very poor packing efficiency. In the sense, you are wasting space. Nothing there. That is the question.
Because UAVs, actually, when we talk about small UAVs, we use space maximum. Because volume is very, comes at premium.
So
you could have made a much smaller fuselage. That is what he is saying. Why have you made such a
Yes,
large
sir.
fuselage with empty space?
Yes, sir. Sir, actually, it may in the image it may look like a bigger one, but in actual it is small. And secondly, we wanted to secure some space in for electronic components. And because previously when we were making the CAD modeling, we were also doing the CG calculations. So we wanted to secure some space that in case if after putting the load, in case if the CG shifts, so that we can get enough space to shift our electronic components so as to maintain the CG.
No, you can shift the whole fuselage if you want to control the CG. You don't have to put additional ballast weight. Your whole fuselage can be relocated forward and backward for CG control. The heaviest part of the aircraft is the fuselage. You can just locate it a little bit forward and backward. So nobody wants you to fix the fuselage at a particular location. Leakage, some background noise is coming. I don't know whether.
Sir, that's it. My question was that only, sir. Thank you.
And
Okay.
sir, I want to add one more point, if you please allow.
Yeah, go ahead. Go ahead,
Yeah.
go ahead.
In the wing, we provided with this rods also, just to in case you were asking the previous question that how the wing the shape will be maintained, and there was a wing in the there's a rod in the middle also, as well as this side stringers you can see from the image to hold the wing in its position.
No, that also that is clear to us. I mean, our doubt is not
Yeah.
that. The question that was asked by Mr. Saurabh Bagare was how will the wing maintain the shape, because all you have is a T frame. So with the T frame,
Yes, sir. Yes, sir.
you are only securing the center of the wing and the edges of the wing. But in between, it can take any shape depending on the wind. And he has already mentioned to you
yes, sir.
that this aircraft is going to deform. And so, by the way, there is a lot of background noise coming. So I think some people have to mute themselves.
Yes, sir. And sir, there is another material which, like I was speaking while answering that question, that material that is used in the collars are called fulcrum material, buckram, something like
Yeah, but
that.
you know, that is going to make your
Yeah.
aircraft very heavy. So the moment you start putting more material in the wing, then the advantages of this Regalo wing is lost. See,
Yes, sir.
the principal criticism is that the Regalo wing
Mhm.
generally is designed to be controlled by flexing the wing. And in your case, you are not
Yes,
at
sir.
all, you are not at all using the wing for uh, any control. You have gone for a rudder waiters, and that is going to create more complications. And if you look at the fuselage, the kind of loads that will come because of rudder waiters at the end of the fuselage, they are going to you will require a mixing unit in your control system. So you are unnecessarily complicating your life by going in for this kind of an empennage. That is what the previous examiner has asked. Okay, I think
Yes,
that's
sir.
sufficient.
Sorry, sir, interruption.
Yeah, I know.
Time.
Time is up. Thank you so much, Namanuddin. So I think in the interest of time, we will stop. So I would like to thank all the participants. In fact, there are so many people in the audience. If the I wish we had some time, but we are already 5 minutes past 12 o'clock, and we were supposed to finish this event by 12. So very thankful to all the student participants who have been patiently answering our questions, and we will get back with the results after having a discussion with among ourselves. So thank you so much for first of all adhering to the time limits. You can see that even with only 5 minutes per team, we have already crossed so much of time. So some of you might have thought, why not give more time to the speaker? But you can actually convey your main idea in 5 minutes. There is no need for you to need more time than that. So I would like to hand over to the organizers if they want to make any closing remarks, because I am through, and I will talk to the judges and get back with the solution. So Manini, if you are there, you can take over now.
Okay, sir. Thank you, sir, for conducting the presentation round. And on the final note, I would just like to thank all the judges, all the guests, and all the participants for being a part of this competition. And I hope that it has been a great experience for you all. As sir said, the results will be given to you through emails. And on this note, we would like to conclude the event.
Hello, Manini.
Yes, sir.
Thank you very much for coordinating the event. And I am very grateful to Air Marshal Sukhchand Singh ji and R.K. Shera, who were present throughout the presentations. I am really grateful. I am also grateful to Goel Saab and Joshi ji, who also are present, Dr. Jimmy as well.
Thank you, sir.
Presentation.
Thank you, Jindal Saab.
Right.
Thank you.
And I am also very grateful to Dr. Sina Matra, Professor Aerospace from IIT Kharagpur, who just left 5 minutes before by calling me. So I'm really grateful. And I am always thankful to all the participants and all the teams, plus all members of Aeronautical Society of India, KP Sharma ji as well. Thank you very much. So should we
We can call off the meeting. I think I would request if possible, Saurabh Bagare and Deepak ji, if you can stay behind, others can sign off.
I am there and I'll be staying.
Yeah.
Okay, I am leaving, sir. Thank you.
Thank you. Thank you. Okay. All others may please leave. Nomaduddin, you can stay with us.
Okay.
Thank you, sir.
Requesting all the participants to leave. Okay, what we can do, Deepak ji and Saurabh, we will have a separate meeting after 5 minutes. Let us just leave this.
Okay. We'll go have freshen up and come back.
Yeah. You can come back in about 10 minutes time. Okay, so I'll just stop this meeting.
Yeah.